Okay, so we're going to start off with some exam stuff, and then we're going to go back through some frustrating ice chart kind of things. Look at some titration curves. Then we'll look at solubility questions, and hopefully we'll be done at that point. So I've definitely cut back a lot of the solubility on the exam because we aren't going to get through as much of it. So this is largely towards only you, apparently. You were the only one here. So I talked to a few people in the tutor center about practice exam number 2 from summer 12, so last summer. And there were a couple questions on it that I said don't worry about. I looked closer at those problems. They are problems that you should be able to solve. Okay, so they were labeled as, I think, 3 and 4, Roman numerals 3 and 4. Both of those are things that you should be able to do. So let's go ahead and take a quick look at those. For that first one, okay, for now our green problem. Which way should the reaction go, left or right? So all it's asking here is what arrow do we put in, left, right, and we'll ignore equilibrium. So no equilibrium here. I want to know directly which direction it's going to go. Okay, why would it go to the right? There you go. Well, kind of. HNO3 is a strong acid. H2O is weak. Okay. So what we're saying is the strong acid completely dissociates, reacts entirely. It won't be formed. So our reaction has to favor the direction away from the strong acid. Okay. We could do a similar argument with the strong base, because there's a strong base in there as well. So we could say because of the strong base, it's going to completely dissociate, not going to form. Okay, so both arguments work in that case. So it's an application of stuff we've already seen. How about the next one? Why should the next one go left? We go through and look at the products on each side. On the right-hand side, we see HCl. What do we know about HCl? Strong acid, so it completely dissociates. It's going to go, the reaction's going to go away from it. Okay? So those two should hopefully be fairly straightforward. You should be okay with those. The last one's a little bit trickier. Okay? When we go through and take a look at that last one, do we see any strong acids or bases? No. So now we actually have to pull at some understanding of what's going on with these. With the first two cases, we looked at the strong acid. Acids are easier to deal with. Okay? What's the equilibrium constant for a strong acid? It's really, really big because it wants to go immediately towards the products. So what we can do is take that information and use it towards our advantage. Our equilibrium shifts away from, or our reaction shifts away from the strongest acid. So we go back to our last question there, or that last part of it. Which side has the strongest acid? Or let's not do side. Which acid is our strongest acid? In the blue one. HF. How do we know HF is the biggest or strongest acid? So I start to give some of it away. It has the largest Ka. Which way is our equilibrium going to shift? Away from our strongest acid. Goes towards the left. Okay? So it's an application of the stuff we've already seen. We just haven't had to deal with those numbers necessarily or in this format. Okay? You are responsible for this because we have talked about it in a couple different situations. And now we've talked about it really officially now.
What is a strong base as well? Does it shift away?
Same idea. Okay. Strong bases are also going to shift away. Okay? We could go through and instead of looking at HF and the acetic acid, we could go through, well here, let me erase everything and circle the two species we could look at. We could look at those two species. Yep, so we'd be looking at officially F minus versus the acetate ion. Okay. So now when we look at that, we're essentially trying to rank based on the bases. which of those is the strongest base? Okay, and to kind of help with that, let's assume we aren't given these Ka values. Is either one of those a strong base? No. So as far as trying to determine which one's the stronger base, we need more information. What more information would we need? We'd have to know something about the Kb. Okay? So in the case of this problem, we could either look at this acids and rank them, which one's stronger or weaker, or we could look at the bases, which one's stronger or weaker. Okay? In this case, we were given information about the acids. So trying to determine the direction of the reaction based on the bases is going to be exceedingly tricky, because we would have to convert the Kas into Kbs to then do our interpretation. Why not just evaluate the Kas from the get-go? Okay. We get the exact same answer regardless of how you want to go through and do it. If you do convert them over to the Kbs, you will still find that your strongest base is the acetate ion, and we still push towards the left.
So it will always shift.
It's always going to shift away from the strongest. Okay? Whether it's strong by definition or whether it's stronger. Okay? So a weak acid and base, it can still shift away from that as long as it's shifting towards something that is weaker. Okay? Kind of makes sense? The next part of it, I did tell a bunch of people that you didn't need to know this one as well. Number 4, that was completely wrong. You should absolutely be able to determine that one. Okay? So go through and look at the structures there. It looks a little bit foreign and different than what we've looked at before because it doesn't exactly fit the rules that we've done. Okay? But it is something that you're responsible for. It is something that you should be able to do. Okay? So try and match it up as best you can to those rules. You should be able to solve it. If you've got questions about it, just ask. Okay? As far as exam 2 goes, it is very crudely put together. There are roughly 8 to 10 questions on solubility out of 30. So only 30% of the exam, if that, is solubility questions. Okay? So most of it is on our acids, bases, and buffers, all that kind of fun junk. Okay? So I'm not going to test you that heavily on the solubility section. Take that for what it's worth. If you want to completely avoid that material, give up on it entirely, feel free to do so. Just make sure you ace every other portion of it. Okay? You'll still get a reasonable percentage at that point. Okay? 50% of it is old exam problems. I do reserve the right to change numbers on that, but 50% is pretty much straight from the old exams, either from summer 11 or summer 12. Roughly another 25% of that is from the homework, either Sapling or Connect. Remember, Sapling and Connect are both testing on ultimately the same types of questions. I tried to make sure they overlapped fairly well. I went through both homework assignments and picked problems relatively equally between them. Okay? Again, numbers can change. The last 25% is stuff coming from lecture or stuff coming out of my head because I didn't feel I asked that question appropriately in the previous exams. Okay? So you get a rough idea of what's happening with exam 2. I will post more information to Canvas as soon as I have more information. Okay? I still have to finish it, finalize it, format it, all that fun stuff. Okay? Questions about that? Yes?
That 25% that's from lecture or your head, does that, excuse me, is that more of like conceptual?
A lot of it is conceptual stuff, but we have worked several problems in lecture as well. So those problems have an equal probability of showing up as well as the conceptual stuff. Okay? Other questions on that? Okay, before I do that, I just want a random survey here, light survey. How many people are sick of ice tables? Not all of you? Come on, be honest. I'm really done with ice tables, and I'm really not looking forward to having to talk more about it today. Okay? When you go through and solve these problems, you're going to have to use ice tables for a lot of them, and you have to be careful on when it's necessary to use them and when it's not. Worst case, assume you use them, you'll always be right. Okay? If you make the assumption that you don't need to use the ice chart or on an ice table, some of the times you'll be wrong, and that's going to get you to the wrong answer. Okay? So worst case when solving your problems, always show the ice chart. So particularly when you're working your homework, go through, do an ice table, draw it all out, spend the effort, and start to generate when you don't need to use it versus when you do need to use it. Okay? And we're going to talk about, in general cases, based off of a titration curve, when it's important and when it's not. Yes?
So speaking of ice table, so I was trying to do the exam thing.
Yes?
I don't know, I'm just kind of confused. When do we use burn thing in the ice?
That's
or
what
when
we'll
do
look
we...
at right here.
Oh, okay.
Yep. So if we look at a simple version of a titration curve, okay, this should look pretty familiar for anybody that's looked at old exams. You'll notice that I definitely cut and pasted or cropped it a little bit weird. Whoa. That should read NaOH at the bottom. That's just how I cropped it. We'll look at a slightly larger version in a second. So what we want to go through and do is use this to kind of help us discover when we can use different problems or not, okay, or solve different aspects. Okay, so to start off with, it might be helpful to identify some important points along here. Okay, so what do you think is happening? Okay, we are adding base, in particular a strong base, to a weak acid. Do we know what the weak acid is? No, so let's come up with a symbol to represent the weak acid. A weak acid needs to have what? What's the definition of an acid? Hydrogen. So if we're going to use a symbol, at the very least we have hydrogen. That hydrogen will be connected to some conjugate base. We don't really care what that is. The standard notation is just to show HA. Okay. Where on this titration curve does HA exist? Okay, for sure at A. Why at A? Okay, that's absolutely where we started. We have HA at that point. Do we have anything else at that point? We've got to be a little bit careful with that. Okay. If we take HA and just add it to water, so no sodium hydroxides there, what's going to happen to HA? It's going to dissociate into the ions, and we get H plus and A minus. So even at this point, at point A, we do have a little bit of A minus. Where's that A minus coming from? Our HA compound. How would we figure out the concentration of A minus? It's not 1-to-1 necessarily. It's only 1-to-1 if HA is a strong acid. It's a weak acid. So we're looking at trying to determine the amount of A minus that is produced from this. Yes? We know it's a weak acid because we decided at this point. Okay. Which is fair. Yeah, it's a nice chart. Okay. So if I wanted to know other information about that point, I would have to use an ice chart. That's how we would determine the pH. That's how we would determine A minus. Okay. So I would have to use an ice chart at that point. Okay. And as far as deciding whether it's weak or strong, we'd be given a little bit more information about that to help lead us into that. At this point, we'll assume it's weak. It's at very least an acid. Okay. Now what can we do? Is there any other point on this curve that we could identify? Okay, we could go through and label the equivalence point. What happened at the equivalence point? Or where is the equivalence point? Let's do that. C is our equivalence point. What happened to get us to the equivalence point? Okay, we got to be a little bit careful on this. This is the moles of the base. The moles of base that we added at that point equals our initial moles of our acid. Okay, so that's valid at that point. Okay, what does that mean? What other piece of information comes out of that? No, we can get to the half equivalence, but we can still stick some more information at the equivalence point. And that's what we did already. Moles of base added equals our initial moles of HA. So it reacted with all of our HA, right? What's left? A little bit close with the base. Be a little bit more specific. It's not just base, it's the conjugate base. At that point, all of our HA has completely reacted, which means all of our HA has turned into A minus. So at that point, I have A minus. Okay. That would be the only species sort of there. We've generated A minus at that point. We could then go through and say, okay, what happens now? What if I want to calculate the pH?
Wait, sorry, you said A minus is the conjugate.
Is the conjugate base of our acid. Okay. To figure out the pH, what would I need to do? Okay. A minus is a weak base. What does a weak base do when it hits water? Dissociates into so if I wanted to figure out the pH at this point, what do I need to do? A minus dissociates to generate hydroxide ion. Does hydroxide ion affect the pH? Yes. How much does A minus dissociate to form hydroxide? Is that dependent on anything? Say like the base dissociation constant, as in maybe a Kb, as in maybe we need an ice chart. Okay. To solve for our pH, we would need to go through and use an ice chart. We've converted everything over to A minus, but now there's nothing to react with it, or it can now react with water. We generate another equilibrium expression. We would need to use that ice chart. Yes? No?
So what would be included in that ice chart?
What do we know is there?
OH.
We know A minus is there. There is no more base because it's entirely reacted with our acid. So the only thing present is our conjugate base. What does the conjugate base do when it hits water? It reacts to generate a little bit of acid, our HA, and OH minus. That OH minus we could then use to determine the pH. How do we figure out the concentration of OH minus? It's dependent on the equilibrium constant. It's dependent on an ice chart. Yes, no? Getting some yeses, so it's an average a little bit better. Okay, hands, that's better. What's up? You tell me. If we look at the equilibrium expression for this, what would it equal? K equals. What are your products? Yep. HA times over. Do we need to include the H2O? Why not? It's a liquid. Are we looking at a base or an acid? A base. What K should we be looking at? KB. Good question. Yes. So that depends. I would have to give you a KA or a KB. You might be asked to convert the KA to the KB. Okay? I would probably give you the KA because what did you start with? An acid. Which means if you get to this point, okay, to figure out if you got to that point, we'll look at the next thing. Okay? You would then need to solve for the KB, so you'd have to convert your KA over to the KB to go through and solve. Okay? How do you know you've gotten to point C from A? What had to happen? pH had to go up. How did the pH go up? You added a strong base to a weak acid. What do strong bases do? Completely dissociate into the ions. Okay? Strong bases will then react with acids. Okay? This is no longer an equilibrium, which means that whole section of material, to go from point A to point B, I need to run a non-equilibrium solve. That non-equilibrium solve, as we've been defining it, is the our barn chart. So to decide, given a question, where we're at on this curve, right here at A, we haven't added any strong base. We don't need to do any kind of barn chart. If I now add strong base, that strong base reacts with HA, and it now shifts me somewhere along that curve. Where on that curve then determines what I should be solving for, be it an ice chart or if we push further up along that curve. Okay? So we would have to go through and do a limiting reagent calculation to determine where on the curve we were. Okay? Once we've got that established, we can then go through and solve an ice chart. Questions? Yeah. We did that yesterday. I'm not about to solve more ice charts like that. You will see a problem like that on the exam, absolutely. You need to be able to solve for a limiting reagent and then shift into an ice chart. Absolutely.
I just don't understand why we picked C as the.
What happened at point C?
Yeah, I get that, but I mean without like the multiple.
No, don't look at that. What happened at C? Compare A to C. In the process of moving from A to C, what happened? As we go through that position, pH doesn't change initially, and now all of a sudden it spikes. Why would the pH spike? Why does your pH go up, ever? Because you've got base present. Why did it not spike earlier? Because there was acid present to prevent the pH from spiking. Why does the pH spike? What happened to the acid present? It completely reacted. There's no acid left for the base to react with, so now the pH spikes because all we're doing is adding base, which means the pH jumps. Okay? And what we're doing is in that workup to that exact point, we've got all sorts of equilibrium issues going on. So we'll pick at the exact instant where it switches, because at that exact instant is when I've added exactly enough base to counteract the acid present. Okay. As I add a little bit more base, that's now going to affect this equilibrium, our blue equilibrium now. Okay. And that's going to continue to prevent A minus from making HA. Okay. Which means our pH is going to continue to go up until eventually we add so much base that A minus can't form any more HA. Okay. Which means the only thing present when we get up to point D, would be, I do blue? Let's do green. What would we have at point D? For sure we have OH minus, because we've been adding that. What else would we have? A minus. Okay, that didn't disappear in the process of that reaction. It's still present. Okay, as far as deciding how would we solve for the pH at that point, okay, what could we do? pH is determined by the concentration of H+, which we know is related to OH-. Do we know the concentration of OH-? Did you just add OH-? Yeah, so you should know the concentration of OH-, which means you can figure out the concentration of H+, you can figure out the pH. Do we need an ice chart? No, why not? We have the concentration of OH. There's no equilibrium. We don't have to worry about anything else. We go immediately into solving from our OH-. What happens if we're a little bit lower? What's the average of green and blue? I don't have an average. Let's say somewhere in here. At that point, I still have OH- and I still have A-. This is where this one gets tricky. Okay, I haven't added enough base to completely overwhelm A- and prevent the reverse equilibrium, generating acid, which means A- is going to contribute a little bit to our base concentration. We'd still need to solve an ice chart, okay, which is counter to what I said before. And that's because what I said before was trying to give you an easy example, an easy out, which is what I'm still going to give you on the exam. If you have excess strong base, what is your pH going to be determined on? The excess strong base. Okay? Because as we add base, we've overwhelmed our weak base. Which one's going to contribute most to our pH? The strong base. Okay? So as far as solving, I expect you to be able to solve up at this top portion. Okay? To solve for the pH, what's the only thing we need to be concerned about? Okay? Just the contribution to the pH from our strong base. Okay? Where it gets tricky for solving is all of the stuff kind of in that curve. Because in that whole curve requires an ice chart. Okay, so when doing an acid-base titration, if you have excess strong acid or base, I am now telling you the problem that you will see on the exam means you do not have to do an ice chart, because what's contributing to the pH? The strong acid or base. Do we do an ice chart with a strong acid or base? No, why not? There's no equilibrium. What does the strong acid or base do? Completely dissociate. There's no ice chart to solve because there's no equilibrium. There's nothing to worry about there. Does that make sense? So it's pushing us further on the curve. Where else will I ask questions? Well, if we pick the easy extreme here, where's the other extreme? Right back at A. What chapter did we solve for A at point A? Oh, don't do that. This was chapter 15. You are responsible for solving that. What did chapter 16 ask you to do? Everything in orange. All right? As far as what I will test you on, we've got chapter 15 at point A. We have chapter 15 at point D, because what's happening at point D, it is just the strong acid or base, exactly what we did in 15. What did we do in 16? 16 was somewhere along this transition, our buffer zone, okay, or where our pH starts to change. We just said that in that whole transition, when we're switching really rapidly from one pH to another, that is a tricky question to solve. What did I just say about what kind of problems I'm going to ask you to solve? They're not tricky ones, which means the questions that you're responsible for, or the areas that you're responsible for, everybody likes purple. Let's pick purple for royalty. Okay, because it's royally not a pain in the... We've got our extremes on either end, our chapter 15. The next big section that you're going to be responsible for is pretty much everything up to that sharp change in the pH as far as calculations go. What's happening in that new purple section right in the middle? What are we looking at there? That is a buffer. To solve for the buffer, okay, there's two ways to generate it. We start with a weak acid and we add strong base, which means we have to go through a barn chart. Or we start with a weak acid and we start with its conjugate base. Okay? In either case, that buffer zone, what we're generating at some point or another, is a little bit of the strong or the weak acid and a little bit of its conjugate weak base. That balance between those is our buffer zone. That's where the pH does not change. To solve, we need to know what those concentrations are. Once we know those concentrations, we can either go through and solve an ice chart or the Henderson-Hasselbalch equation. Okay? Because what happens is that we expect such a small change in our pH that it doesn't affect the overall equilibrium concentrations or our initial concentrations enough that we don't have to solve the ice chart all the way through. It's entirely up to you what you want to do. So in that buffer range, if we see a strong in the question, if you see strong, that means you must do barn. Okay? If you don't see strong and you have the pairs, you're in that buffer range because you have a weak acid and a weak base. What we're looking at is a Henderson-Hasselbalch equation. We don't have to do the barn chart because we're already given our initial concentrations. The concentrations that we can plug in to use the Henderson-Hasselbalch. If we don't want to use the Henderson-Hasselbalch, we can use an ice chart. Does the exact same thing. Okay? Yes, that's when we're looking at weak acids and weak bases. Okay? Why go through all of this? Being able to look at an individual titration curve is massively important. Any standardized test that you're going to take is probably going to ask you questions about the titration curve. Okay? Because it's really easy to interpret graphs. Whereas if we take a look at the effort that went into interpreting all of the barn and ice charts, how much mathematics do we have to do? We covered an entire board with one problem. A titration curve does an infinite amount of those problems. I can then pull useful information off of the titration curve without having to go through all of those mathematics. Okay? So with this titration curve, we've identified a couple important things. What's happening at point A, C, and D. We haven't talked about B yet. We'll get back to B in a second. Any questions about anything that's up there other than B? Yes?
You said at D we don't need to do an ice chart because it's a strong base?
Because it's a strong base. There's no reason to...
Point A, we have a strong acid.
You do not have a strong acid.
Oh, it was a weak acid.
It's a weak acid. If we started with a strong acid, then you'd still go through and solve it as a strong acid. Then you don't have to do an equilibrium. In this case, we said it was a weak acid, which means you have to go through and solve the ice chart. With a strong acid or base, you are still technically solving an equilibrium. It's just that the equilibrium constant that you're using is infinitely large. So with it being so infinitely large, you end up having to not worry about solving an ice chart. You can simplify it. Yeah?
And then right there in the buffer area, how it said strong, we do the barn.
Yes.
That adding, is that if we add strong acid or base depending on?
Yes.
Okay, that's whatever's added, right?
That's whatever is added. If you add a strong acid or base to a weak acid or base, you have to go through and see how that strong acid affects your weak acid base concentrations. Then you've got initial concentrations that you can work with. Now you can either solve an ice chart or use the Henderson-Hasselbalch. Yes?
I understand like what we just went through and how you need to solve them, but what values or like numerical values are you going to give us when we're solving for these? That makes
So
sense?
when you're solving for these, go back to what we looked at yesterday.
Okay.
You saw 5 problems.
So they're
That's
gonna,
it.
Okay, so they're not going to be given off. You're going to give us the graph, or you're going to give us like what you did yesterday? I'm just confused as what we should.
So
wanna see.
you need to know how to interpret a titration curve, because
Okay.
the titration curve allows you to understand information without having to solve stuff. You also need to be able to solve stuff. That's the other part of this class. So what we've gone through and done is looked at it from 2 perspectives. All the mathematics, which we looked at yesterday, and now no mathematics. What information can we pull off of that curve? You were responsible for both those interpretations.
Okay, so if we're actually doing the solving, it's going to be stuff that we were doing
You'll do,
yesterday.
yep,
Okay.
exactly right. Okay. Other questions on this? Okay, when it comes to the Henderson-Hasselbalch equation, why does it end up working? Okay, it's the same thing as an ice chart. If you break down an ice chart into the individual steps, what you end up doing is solving the Henderson-Hasselbalch equation. Okay, it is the exact same thing. Okay, at no point is it actually different. We've just jammed all of the calculations that you've done in an ice chart and put it in one fell swoop step. Okay? So if you're starting with a weak acid, you can generate this Henderson-Hasselbalch version. This is the standard one that almost everybody refers to as the Henderson-Hasselbalch equation. Why do we look at this one? Because we typically look at acids. Okay? So that's the one that gets referred to as our Henderson-Hasselbalch. If we're given a weak base, okay, so we titrate a strong acid into a weak base, we can go through a very similar situation, except when we go through and solve this, instead of it being a pH, because it's an acid, it's now a POH, because it's a base. Instead of it being a pKa for it being an acid, it becomes pKb because it's a base. Okay? The solve is exactly the same. You'll notice that we do see a difference in the alignment of those 2 species, and that comes from the Kb or the Ka expression. Okay? So you can go through and solve that algebra to see that both of those equations should hold true. Yes? This is where the Henderson-Hasselbalch picks up a huge advantage. The concentrations that we pluck into it. What are those concentration values? Those are the initial concentrations of our buffer. Okay? Why does it work out? When you go through and do the ice chart, you run the assumption that X is really, really small, which means the initial concentrations don't change. Hence, we can get away with it. So as long as you're in that buffer range, the Henderson-Hasselbalch equation works. As soon as we shift outside of that buffer range, what happens? Henderson-Hasselbalch fails. Okay? Because we're making an assumption to get both of these to hold true. Yes? Yeah. Okay. I will provide, I don't think it's actually on the equation sheet that I sent out or that posted. I will give you the Henderson-Hasselbalch, the standard one, our acid equilibrium. So pH equals pKa. That will make it onto the equation sheet. If for some reason it doesn't by the time of the exam, that's because no one reminded me and I forgot during the exam. Raise your hand and I'll draw it up on the board. Okay? So you do not have to memorize that equation. You also don't have to use it. It's entirely up to you. Okay? It is commonly messed up by students. There are some faculty that don't actually show the Henderson-Hasselbalch equation because people misuse it. Okay? It is only valid during the buffer situation. Okay? So why does it end up being useful? So let's take a look at one more pH curve. What can you tell me about this curve? What are we starting with? An acid, good call. So we could start with HA. Is it just HA? Why is it H2A? There's two waves is one way to describe it. What happens when H2A hits water? We get H plus and, whoops, HA minus. What happens when HA minus hits water? We get H plus and A minus 2. Okay? So as we add base, what's initially present? Well, let's go, now let's take our information and start to plug this in. What do we? H2A. How would we solve, given a problem for a pH? Need to go through and use an ice chart. Okay? I slowly start to add base. What happens? The base pulls away H plus from our equation, our very first one. The equilibrium is messed up, so now H2A says, fine, I'm going to give you more acid. So it generates more H plus. So we still have H plus in the solution. Our pH doesn't change much, so it levels off. Then all of a sudden it spikes. Why does it spike? Okay, we've run out of H2A. So there's no more of that initial H plus. So what happened at point C? So we could say the moles of our base equal the moles, initial moles of H2A. What else can we say at that point? What's present? Just HA minus. We could also call this the equivalence point if we wanted to add that information onto this. Okay. What happens as we continue to add base? You'll notice the pH spikes, but then it slows down again. And you'll notice that it's slowing down again around pH 8. So it's not the pH of a strong base. That seems a bit odd. Why would it slow down below the strong base concentration? The base is reacting with another acid. HA minus has some acidic hydrogens. So as we add more base, the base pulls this hydrogen off, and what happens? Equilibrium's messed up. HA minus generates another hydrogen. Says, ha, I'm not going to shift the pH anymore. And we get yet another level off, okay, through point D. Then what happens? We continue to add more base until eventually we've added so much base that we can't get rid of the HA anymore. And we reach point E. What is point E? We have a second equivalence point. At that point, the moles of OH minus, okay, or the moles of OH minus added equal moles of our HA minus. Okay, it's a little bit harder to say the initial moles of HA minus. Okay, what else could we refer to? If we go all the way back to H2A, what would our relationship be now? It would be twice the moles of H2A. Why? H2A had two hydrogens. The number of moles I added continued to increase all the way through until I reacted with both hydrogens. Okay? So if I wanted to relate it all the way back to my initial concentration, I could. Okay, and that's where we could slide in an initial. Up here we could say at point C. hard to say initial at that point. What happens at point F? What do we have? We have A minus 2 and technically OH minus. You'll notice that our pH is now starting to level off, where we would expect the pH to level off for a pure hydroxide solution. Okay. What other information can we pull from this graph? Are there any points we have not yet labeled? B and D. Let's go all the way back to B, because I think B will be a little bit easier to evaluate. What happened at point B? We're in the buffer range, so we could tag that in there. pH equals pKa, but why does the pH equal to pKa? Because what? Half of it's used. I can accept that. Because the concentration of H2A at that point equals the concentration of HA minus. How do we know that? We're halfway between becoming entirely HA minus. Okay, so our concentrations must be equal at that point. At point A, it's only H2A. At point C, it's only HA. Halfway on my way there, what happens? The concentrations must be equal to each other. Because as I get rid of H2A, where does it go? To HA. Because of this equality, we now know that the pH at this point is equal to the pKa. We want to add a little bit more information because we see a second equivalence point, which means there's a second hydrogen. Which hydrogen was this one? The first one, so we'll call it the pKa1. What happens at point D? We're still a buffer. We can now say that the pH at that point equals pKa2. Why do we know that to be true? Because we're halfway on the way to becoming HA minus equaling, A minus 2. Did I do the minus 2 earlier? All right. We give special names to our buffer points, B and D. What's that special name? It's our half equivalence point. Because we are halfway on the way to being our equivalent point. Okay? Pretty huge for our titration curves. Okay? Because we're running out of time, I'm not going to take any questions on that. That is pretty fully labeled. Okay? When it comes to solubility, in 151, we went through very particular rules. It was either soluble or insoluble. We didn't have any kind of gray area. When we move into 152, we're going to change that up and say everything has some solubility. Some have more than others. If it's completely soluble, we don't have to worry about it. What we're going to be concerned about are those ones that are only slightly soluble. Okay? Meaning, according to 151, they were insoluble. Okay, so the equation that we end up using is looking at that solid and looking at it dissolving into the ions. And we get an equilibrium expression. Okay. What's special about the concentration of silver chloride? It's a solid, which means the concentration doesn't change. It's constant, and we get K equals to the concentration of our ions. Why did we not look at the reverse equation? Why did I not, whoops, you were going to do that to me. Why did we not say Ag plus plus Cl minus going to Ag solid in equilibrium? What's that? No, because it's arbitrary. We can decide whatever we want. If we set up the K for this case, we'd get Ag solid on top, Ag plus plus Cl minus, whoops, not plus, times each other. What's the effective concentration of silver ion and chloride ion? If this is an insoluble solid, what's our concentration of our ions? 0. What's 1 divided by 0? Okay, depending on what mathematician you talk to, you get different answers. Okay, it can be close, it approaches infinity. Some people say it's 0. Some people say it's 1. Okay, which I'm not sure about that 1. But I've heard 0 and infinite for this. Okay, that makes it mathematically really difficult to solve. So what do? We don't set up our equation that way. Okay. Because it's all set up as it is, we can go through and run our equilibrium expression like this. Because we're now looking at the solubility of an individual solid, and to get this expression, I had to multiply our equilibrium constant times the concentration of our solid. We change that K to something else. We will call it K SP, S standing for solubility. Well, that makes sense. We're looking at the solubility of a compound. What's the P stand for? Product. How are we solving for this? We take the product of our concentrations of the ions. Okay? So when we're moving to solubility questions, this is what we're looking at. You'll see KSPs. Okay? It's the same exact idea behind everything else that we've been doing. They're still equilibrium expressions. They are still, unfortunately, ice charts. Okay. After Monday, we won't have to worry about ice charts for a while. Okay. So let's go through a general idea on what's happening with solubility. Okay. So let's take a look at 2 examples. What happens to table salt when it's added to water? It dissolves. Since this is 152, we could throw in an equilibrium arrow. Is that equilibrium arrow really representative of what happens? No. Okay. So we would typically show a unidirectional arrow on that. How about when we add sand to water? If we assume it works, say the sand dissolves in water, so our sand solid becomes sand aqueous. Does sand dissolve in water? No. So is an equilibrium arrow a good option? No. Okay? So really what we're looking at is those shifts. If we tried to go through and do equilibrium expressions for these, what would the size of the equilibrium constant be for sodium chloride? Big or small? Really, really big, because completely dissociates into the ions. We have no concentration of reactant. It means our product concentrations are huge, and we get a massive equilibrium constant. What about the equilibrium constant for sand? Be darn close to 0, because sand doesn't dissolve in water. Okay? So what we're evaluating is those relationships, and now bringing in our equilibrium constant expression idea into these. Okay? That's our goal behind solubility. Okay? So we're always going to be looking at those 2 expressions. Okay? Were there questions about that? Okay. So, where we've got to be a little bit more careful is where we're dealing, or when we're dealing with our units when we're looking at solubility. Okay, this is particularly going to be a problem, I think, with your homework problems, not so much an issue when it comes to the exam. When we use solubility products, okay, or any equilibrium constant, what units are we using? What equilibrium, or what units did we put into our equilibrium expression for an acid? Molarity. It's a concentration, a moles per liter. Okay? When we move to solubility, solubility is a really, really, really old science, if you will. Okay? Because it's so old, it happened before we had any real idea of what a mole was. Which means when they went through to solve and work with these things, they used different units. Because if we can't measure moles, why would we use that unit? So what did they end up using? Grams, because it's easy to mass things, and the volume of whatever solvent you're using. Typically shown in milliliters, but it might be liters as well. Okay? So watch out for the units used in your problems. If they give you grams per milliliter and they want to know a KSP, or which we'll look at in just a second, an equilibrium constant expression, we have to convert those grams per milliliter into moles per liter every single time. Okay? So go back to your 151 conversions and just make sure you do that. How do we convert between grams and moles? The molecular weight for each of our compounds. So we'd have to determine the molecular mass by using the periodic table, add it all up, and get that mass. How do we convert milliliters to liters? Okay, 1,000 milliliters is 1 liter. Make sure you've got these conversions down. I would recommend writing them out because 9 times out of 10 you'll accidentally mess them up. Okay, I'll accidentally mess them up. Okay? So make sure you answer according to what units are being asked, which kind of brings up a point with the sapling homework or Connect homework, any online homework system for that matter. For sure you need to answer the question asked. Now you have to worry about the units of the question asked. So make sure you answer appropriately there. The last thing to be careful with when entering things into an online homework system, significant digits. Just because your calculator spits out 20 digits doesn't mean Sapling or Connect wants 20 digits. Okay? Go through and make sure you use the appropriate number of digits. I have not seen a homework system enter improperly their significant digits. Okay? They always do it correctly. Okay? Which means if you add one too many sig figs, likelihood that you get it wrong is pretty high even though you answered it correctly. Okay? So watch out for that. Other definitions that we might come up with or see. We just talked about the solubility product, okay, just multiplying those. The other thing that we can think about is saturated. Saturated solution means that we've entirely dissolved the solid. Okay, so there is no solid left. This means it is one molecule under our equilibrium constant maximum. What happens when we add one molecule more? Now it can't dissolve. So what happens? It precipitates. And that's when we have one molecule over the equilibrium constant maximum. Why does this become important? How do we solve for one molecule under or over? Go all the way back to 151, and we could add one molecule worth of molecular weight to our mole count, and we'd be one atom over. How much of a significant digit figure would we need to be able to record that difference? Probably need a lot of digits. We're probably pushing out to the 23rd order. Okay? So what does that mean? If we're being asked to solve for a saturated solution or a precipitation, okay, what are we going to solve for? The equilibrium constant. We go all the way back to the exact same thing. We're only working with the equilibrium constant. If we want to know what concentrations that we can get up to before it precipitates, solve for the equilibrium expression. Okay? If we want to know what concentration we need to get to for it to all dissolve, what do we solve for? The equilibrium constant. Okay? We don't add or have to worry about that one molecule over or the one molecule under. It's the same idea all the way through. Okay? Because that one atom or molecule doesn't make enough of a difference in the mole count to make our molar concentration different enough to make it worth reporting it as that difference. Okay? So, pretty sure we've got two problems here. I'm going to walk through both of these in the interest of time to make sure we see them both. Okay, a 500 ml solution was saturated with calcium oxalate at 25 degrees Celsius. When water was evaporated, that number of calcium oxalate was obtained. What is the equilibrium constant that describes the solubility of this compound? Okay, so the first thing that we could go through and do, be an equation. And actually before I do this, I'm going to stop the video because I don't want it to delete everything.